Hello and welcome to another episode of TWiML Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. Earlier this week, I had a chance to speak with Chris Shallue, senior software engineer at Google AI, about his project and paper on exploring exoplanets with deep learning. This is a great story. Chris, inspired by a book he was reading, reached out on a whim to a Harvard astrophysics researcher, kicking off a collaboration and side project eventually leading to the discovery of 2 new planets outside of our solar system. In our conversation, Chris and I walked through the entire process he used to find these 2 exoplanets, including how he researched the domain as an outsider, how he sourced and processed his dataset, and how he built and evolved his models. Finally, we discussed the results of his project and his plans for future work in this area. This podcast is being released in parallel with Google's release of the source code and data that Chris developed and used, which we'll link to in the show notes. If what you hear inspires you to dig into this area more deeply, you've got a nice head start. This was a really interesting conversation, and I'm excited to share it with you. Before we jump into the interview, a reminder that the next TWiML online meetup is quickly approaching. Be sure to join us next Tuesday, March 13th, for an in-depth review of reinforcement learning and the Google DeepMind paper, Playing Atari with Deep Reinforcement Learning, presented by meetup member Sean Devlin. Head on over to twimlai.com/meetup to learn more or register. Okay, let's get to it. Hey everyone, I am on the line with Chris Shallue. Chris, welcome to This Week in Machine Learning and AI.
Thanks, Sam. Happy to be here.
Awesome. Why don't we get started by having you tell the audience a little bit about your background and how you got interested in machine learning?
Sure. So I started out studying mathematics, actually. In my undergraduate degree, I did a double major in pure and applied mathematics. And once I graduated, I then did a year of research in pure mathematics, studying certain classes of polynomials, in fact.
Oh, man. I'm starting to break out in like sweat here. I think in grad school, the real analysis class I took was like the hardest class.
Right. Well, I was actually studying these polynomials over finite fields. So it was more in the abstract algebra space. But to your point exactly, after I did this, I decided I wanted to do something with more of a concrete application in the real world. And so I knew I wanted to do a PhD, and so I looked at some other options, and eventually I decided to pursue a PhD in biomechanical engineering.
Oh, wow.
So I started that PhD, but after about a year, I decided that perhaps a career in biomechanical engineering research wasn't for me. So I started to look for other opportunities at that point. So briefly, I went back to mathematics for a little while by teaching classes at my university. But I decided to apply for a job at Google, mainly because I was excited by some of the really high-impact, world-changing projects that I was hearing about coming out of Google. In particular, I remember being excited by Project Loon. So for those who don't know, that was a project, it's actually still going, that tries to use networks of flying balloons to bring the internet to users in rural and remote areas. So I applied to Google and I was hired as a software engineer, but unfortunately I didn't get to work on Project Loon straight away. I was actually placed in the Google Display Ads team, and I was working on ads for Google Maps and Gmail.
Okay.
And this is where I got my first taste of machine learning. I was actually working on models to try and show the most relevant ads to each user, and I learned a lot about machine learning in that role. And then early on in my career at Google, I saw a presentation here at Google by some researchers in the Google Brain team where I currently work, and they had created a neural network that would automatically generate image captions. And I thought this was really exciting. This model that they created could accept raw pixels from photographs and output fully formed English sentences that would describe the photo. And so this model was actually trained using only images and captions as input. So quite amazingly, the model was not actually given any details about the English language except the captions. And it actually managed to learn not only how to caption images, but also how to write, sentences with good English grammar, which I thought was pretty amazing as well, just from reading captions. And so at that point, I decided I wanted to work on the Google Brain team. And luckily
Nice.
I got the chance to transfer to the Brain team after 2 years in ads. And since then, I've been working on machine learning research here in the Brain team. And I've been lucky enough to work on many different areas of machine learning research since I joined the team.
Awesome. And one of the areas that you did get to work on, you got a little bit of publicity on. This it grew out of really a side project or a hobby project. Is that right?
Yeah, that's right. Actually, this project that I've been working on to discover planets with machine learning really grew out of a random sort of chance idea I had while I was reading an unrelated book. There's a book called Human Universe by Brian Cox, which is mainly about exploring our evolution as a species, but it also digs into the question of whether we are unique in the universe. And one of the fundamental pieces to that question is whether there are other planets like Earth out there and how many there are. And then one of the things he mentioned in this book was that it's actually quite difficult to detect these planets in sort of around faraway stars. And one of the difficulties is actually digging through this huge amount of data that is collected by modern satellites. And so when I read that, I instantly connected that back to my work at Google, where we train models to dig through large data sets all the time. And so I wondered if perhaps we could apply some of those same techniques to dig through these large astronomy data sets and look for exoplanets.
Nice. And this is interesting to me. I've interviewed several people who have come from physics, including at least one astronomer, Josh Bloom, who's at GE Digital now, who have, started from this kind of deep domain knowledge and, learned machine learning and applied it to what they're doing. But you're coming at it from almost the complete opposite approach. Like you have some machine learning tools, and then you hear about this really interesting problem in astrophysics, and you get involved and you actually do something really interesting with them. How did you get started?
Well, you're right that I actually don't have very much background or knowledge in astronomy at all. In fact, I still don't. And so the first thing I did was I jumped on Google and started looking for what these data sets actually looked like and who worked with them. And I was lucky enough to stumble across the name of an astrophysicist who was at the time working at Harvard. His name is Andrew Vanderberg, and he seemed to be someone who had dealt with these data sets in which we look for planets. And so I literally just sent him an email and said, hi, I work at Google in machine learning. Would you be interested in collaborating on a project together? And he actually was interested. And so this whole project has really been a partnership between Andrew and I, where I have taken care of the machine learning side and the coding side, and he is taking care of the astronomy side.
Tell me a little bit about the timeline of the project. How long have you been working on this?
So I believe I started working on this project in late 2016. So around September or October, I believe I first emailed Andrew. And initially I was working on this, as you mentioned at the start, as a side project. I was really just devoting 10 or 20% of my time to this for a few months. but it was around March or April in 2017, so perhaps 6 months later, that we had managed to train a model that we thought we might be able to use to search for new exoplanets. And when we ran this model on a very small sample of stars, we actually found that we were able to discover some new signals that probably were exoplanets. And that's when we started taking this project a lot more seriously. And then I started working on it probably more towards 100% of my time. And so then for most of last year, for the rest of 2017, we really went back and carefully trained our model again and used it to actually carefully search these stars. Andrew did the validation of our new planets that we discovered, and then we wrote the paper, and that was published in January of this year.
We'll dig into kind of how things shifted when you started working on this full time, but I suspect that there are a lot of folks out there who know some machine learning, maybe have taken a deep learning course or work in it and would love to apply it on a project like this. And so I'm really curious if you can dig into like those first 6 months or even those first 6 weeks, like when you're spending just 10-20% of your time, kind of equivalent to what folks might have to work on a project like this in their nights and weekends. Like, how did you approach it, and what were some of the things you did? What did the data set look like, and how did you set priorities for making progress with this?
Sure. So actually, when I started, I had this vague notion that we would use machine learning to search for planets, but I didn't even know what the data looked like. I thought that what we might be doing is training a model to input photographs from the sky and actually look for the actual planets in images of the sky. Mm-hmm. But it turns out that's not, in fact, the way that most exoplanets are discovered.
Okay.
So the format of the data in this case, it's actually not images of the sky, but rather we look at how the brightness of a star changes over time. And so if you're monitoring the brightness of a particular star in the sky, and if a planet happens to pass in front of that star relative to the telescope that's recording the brightness, mm-hmm. you'll actually see the brightness of that star dip down while the planet is blocking some of the starlight. And then the brightness will then increase again, once the planet is no longer blocking any of the light from the star. So the data that we're looking at is actually a time series of brightness. And what we're looking for is certain patterns in that brightness time series that would correspond to a planet passing in front of the star.
Do you get it as a time series of brightness because it's been pre-processed from the state that you previously expected it to be, meaning there have, some telescopes have captured images, and within those images, individual stars are identified, and some brightness value is calculated and kind of logged off into some time series data set? Or is there something else happening to produce that data? Do you have a sense for that?
Yes. No, you're exactly right. So what happens is this data set has actually been pre-processed by a team at NASA. So the data originally comes from the Kepler Space Telescope, which was in operation for the main part of its mission for 8 years. Okay. Beginning in 2009, I believe. Yeah, the main part of its mission was in operation for 8 years, beginning in 2009. But it was looking at the specific section of the sky that we've been searching for the first 4 years. So there's this 4-year data set from the Kepler telescope, and a team at NASA has already taken that data, has localized the stars in that data, and converted that data into these time series, and has actually posted that for free on the internet. You can actually download it. It's it takes up several terabytes, and in fact takes several weeks to download, because you don't get great download speeds.
Even if you're on a Google LAN?
Yeah, even if you're on a Google LAN, yeah, it's millions of files, and we literally just had this big wget script that would just download all these individual files, and it took about 2 weeks to download.
Okay.
But that was going back to your original question here. That was one of the ways in which we were very lucky in this project. A lot of the data pre-processing was already taken care of by NASA. And so not only that, but we were also lucky in that we had a large training set of labeled examples from astronomers at NASA and at other universities. So I mentioned that this telescope was launched in 2009, so over 8 years ago. And in that time, a lot of human astronomers have looked at certain patterns in this data set and have labeled them essentially as being, this is a signal that is a planet, and this other signal is not a planet. So that was one of the other ways in which we were lucky. We didn't have to start from scratch with no training set. We actually had the data, and we had a training set there that was already made for us. And those two reasons are probably key for us being able to make such rapid progress, and within about 6 months having all the pieces together and being able to find some new planet candidates. So I know that there are many other problems in, for example, astronomy, that do have large amounts of data available, but perhaps that data is not in a form that is easily ingestible by a machine learning model, and also perhaps there is not a training set of labeled examples that you can use to train a machine learning model. So I think those considerations are very important. If somebody is trying to, in their spare time, train a machine learning model to, accomplish any task, the two things you want to ask yourself is, one, does this data exist in a format that I can, obtain easily and process myself? And two, is there a training set that I can use to train my model?
And can you tell us a little bit about the model development process? How did you approach that?
Sure. So my process when I develop a model is to start simple and then try and build that up into something more complicated. And so the simplest thing that I thought I could try with this model was simply a linear logistic regression model, which is a very common and well understood type of machine learning model that has been used for decades successfully in a lot of tasks. And so I had this this data from NASA, this time series of brightness values, and so the first consideration there was, how am I going to feed this data into my model? And we can perhaps get into that a little bit more. But once I had figured that out, I thought, well, let's just try the simplest model I can possibly think of. And I think as a general rule of thumb, your simple model should at least get you part of the way there, perhaps even most of the way there. And so we were actually able to train this simple model to actually have relatively good accuracy. The simple model that we ended up training first actually ended up having an accuracy of about 92%. And then, several months later, when we trained our, big complicated neural network model, that model ended up having about 96% accuracy. So I think the lesson here is that you can certainly start simple, and you'll probably get most of the way there before you start trying these really complicated models.
Now, you talked a bit about the data set, but what did the labels look like? I'm envisioning, so you've got these you've got stars and you're trying to identify whether the stars have planets. Are the labels, yes planets, no planets, or are they, numbers of planets? Because part of what you were able to do with this research is identify new planets in known solar systems, meaning stars that already had existing planets, right?
Right.
So I'm imagining the labels have to be somewhat more nuanced than binary.
Right. So if we imagine that the data for a single star is a very, very, very long time series of brightness measurements. Actually, the individual inputs to the model are not that entire time series, but they're individual events on that time series that some other, separate computer algorithm, a very basic algorithm that's not machine learning at all, has gone through and has identified certain events on that time series where the brightness decreases. So as you said, certain stars can have many events where the brightness decreases. It may have many planets, but it may also have something called star spots, which is like a dark spot on the star. And because the star itself is rotating, those dark spots, when the dark spot rotates into the view of the telescope, that's also going to cause the brightness of the star to decrease.
Right.
So there are many different types of events, some of which are astronomical, some of which are actually instrumental, that can cause the brightness of the star measured by the telescope to decrease. And so when I'm actually talking about labels, I'm talking about a label for a particular event on the star where we've actually observed the brightness decreasing.
So that label is just brightness decreasing, or is it brightness decrease because of a planet?
Yeah, so the label is the second option you provided. So one of the possible labels is brightness decreased because of a planet, and the other possible labels are brightness decreased because of some astronomical event, for example, a star spot. And then the third possible label in the data set is that the brightness decreased for some sort of instrumental reason. Perhaps there was some noise, instrumental noise, or something like that. And so when we trained the model, so those were really the only three labels in the data set that we were given, that we started with.
Okay.
But when I trained the model, I actually I binarized this. So one label was this event is a planet, and the other event is this event is not a planet.
Can you give me a sense for, how long did you spend kind of familiarizing yourself with the data set and maybe learning a little bit about the background of the problem and the domain knowledge you might need to solve it, versus modeling, versus applying your model to unlabeled data, that kind of thing?
Sure. Yeah. So I mentioned, I think that it was about 6 months before we had actually trained a model and started discovering planets. And certainly I would say that at least 4 to 5 of those months were me trying to understand this data, to actually, not only download it, but being able to open this file format, right? Like what format does a brightness plot of a star come in from NASA? It ends up coming in a file with a .fits extension. And so you need to be able to figure out how to open that extension and how to extract the data that you want, and then actually how to pre-process that. Luckily, I had Andrew, on the other end of the phone, who already had a lot of experience with this, which really helped. Which really helped me. But nonetheless, I spent a lot of time just learning how to actually use this data and what it meant. I spent a lot of that time reading papers as well. There have been other people who have applied machine learning to similar problems, and so I need to understand what they did. I don't want to reinvent the wheel. I can try and learn from their mistakes and also the things they did that worked well. And so, once it actually got to coding the model and training the model and testing the model, that was really only probably one out of the first 6 months.
Wow. What were some of those things that you learned from other attempts that you applied to your own modeling process?
Sure. Yeah. So there are several steps that are fairly standard in astronomy for processing these brightness time series. The brightness time series are typically called light curves. So I'll just start using the word light curves for them now. So the first thing you actually need to do with a light curve is you need to flatten away what's called the stellar variability. So it turns out that the variability or the light from a star is not actually going to be constant over time. For various reasons, the brightness that you'll measure from a star is actually changing over time quite naturally.
Meaning independent of an event, the star's getting further or whatever.
Well, yeah. There's several reasons. The star is itself rotating. So perhaps different areas of the star's surface are brighter than other areas, and so when the star rotates, the brightness that you see actually changes. Also, there's instrumental effects here that can also cause the sort of the baseline brightness to kind of drift over time. That's actually characteristic of the instrument on the Kepler telescope. So you need to fit away this kind of variability that you see in the brightness of the star. But you want to do this in such a way that you don't actually fit away the events that we're trying to classify, which is when the brightness decreases kind of more sharply and suddenly. So there are various techniques to do that, and so we were able to use some of those techniques in order to sort of normalize the brightness of the star, so that outside these events we're looking at, the brightness was totally flat. So that was certainly one of the key starting points for us.
Were these other techniques machine learning types of techniques, or more simpler data massaging types of approaches? Right.
So the current state of the art system for classifying these events as being planets or not planets is actually it's called the Robo Vetal. It was developed at NASA, and this is actually mainly not a machine learning technique. There is one component inside this Robo Vetal that uses a machine learning technique, but for the most part, it's actually a decision tree that has been sort of crafted and honed by humans. So this piece of software, which was developed over a few years, actually runs hundreds of different heuristics on these events, and it has all these different thresholds and branches to determine whether this event should be classified as a planet or not. So that's the main technique that is actually used at the moment. There have been some other techniques that did the problem, or that took on the problem that we were focused on. One of those used a random forest model, and another one used a sort of unsupervised clustering type model. And so we were sort of one of the first to decide to use neural networks for this problem.
Coming back to thinking about your labeled data, which you mentioned you kind of binarized, you turn into, is this event on the light curve due to an orbiting planet or not? How do you get from that to being able to detect new orbiting planets on a known star that has, on a star that already has known orbiting planets? Or was that a consequence not necessarily related or produced by your algorithm?
Sure. So I think I mentioned that these events that we detect on the light curve where the brightness dips are actually produced by a completely separate algorithm. And traditionally, what would happen was that the astronomers would run some algorithm and would take a whole large set of these events that were detected and manually examine each of them by eye and decide which of those were caused by planets and which of those were caused by various other events. Mm-hmm. And so because this process was the time required was really dominated by the fact that the humans had to go in and examine these things, it wasn't possible to examine every possible signal. So what they did was they set some threshold and said, okay, we're only going to examine events detected above some certain signal to noise threshold.
Okay.
And so now even with the signal to noise threshold, they still actually had to go through and examine over 30,000 events.
Oh, wow.
From the 4-year Kepler mission. So it wasn't like they chose a really, really aggressive threshold, but the possibility still remained that if the threshold was lowered just a little bit, and some of these lower signal to noise events could be considered, that there may be some planets that were missed by the previous searches. And so that's what we looked at in this project. We took our trained model and we used that model to go and look at these events that had not previously been classified because the signal to noise was below the traditional thresholds. And so that was how we were able to discover new planets around stars that had already been searched multiple times before.
Did you run the algorithm against kind of all of the remaining data, and thus we collectively now have a fairly high confidence that we found all of the possible exoplanets, or was because of the data volume or whatever, you also had some threshold or some slice of the data, and there's still an opportunity to apply it more broadly?
So out of the 200,000 stars in this data set, we've actually only run our model over 670.
Wow. Okay.
So we chose those 670 because those stars had already had multiple orbiting planets discovered around them. And it's a lot more likely that you're going to discover more planets around stars that we've already discovered planets around than if you just chose some random star. So we really chose these 670 because we just wanted to, have the quickest test of our model possible. And so we restricted ourselves to this tiny sample and actually, discovered 2 new planets, and we were very excited about this, and we decided to stop and write our paper. But certainly what we're currently doing right now is working on ramping up our current pipeline to actually search all 200,000 stars. And, who knows what we're going to find when we do that.
Mm-hmm. Talk a little bit about the process and approach you took once you switched gears from the more traditional approach to applying a neural net. I think you said you were using logistic regression originally.
Right, that's right, yes. So the logistic regression model really just took in, say, one of these light curves, one of these time series, and simply used those as features. Each independent point on the light curve was an independent feature to the model. And so the model could learn, for example, if this particular pixel, we fed the events into the model such that we'd normalized where we thought the light the light was decreasing, we actually sort of like centered the event in the input. So the model knew where the event was supposed to be. And so the model could learn things like if this particular pixel has a brightness below average, that might contribute to a classification of, it being a planet or it not being a planet. But essentially in the logistic regression model, each of those individual pixels was going to be considered independently of all the other pixels. Essentially, they were all going to be used as independent indicators of whether this time series, this light curve, was a planet.
And so your input vector to the logistic regression model was a vector of kind of the 4 years worth of these brightness values for a particular pixel at whatever time increment they were captured at?
So we didn't actually feed in all 4 years of data in one very, very long vector. What we did was we actually fed in just one of the events, basically, that we were looking at. So we really kind of like zoomed in on the light curve of the particular event that we wanted to know the classification for. So the dimensionality of our input vector was something like 1,000 time series points, as opposed to all the time series points over 4 years.
And did you presumably you knew where the event was, so you bracketed around it?
Exactly. We made sure that in our input, the event that we were considering was centered.
Got it. Okay.
Yeah. So moving from sort of the simple model, the logistic regression model, so one parallel we noticed with this problem is to the problem of classifying objects in images. So with an image, your input is actually a two-dimensional grid, but what you're doing is essentially looking for local patterns within that grid. Local groups of pixels will together form, edges and shapes and images. And so what we had a one-dimensional grid or a vector, but we were also looking for local patterns, in the grid. We were looking for shapes in which the light would gradually decrease as the planet sort of passes in front of the star and then gradually increase again, sort of like a U shape. And so with that parallel to image classification, we decided to use a convolutional neural network, which has been very successful for image classification in the past. And the only real difference here is that our inputs are one-dimensional rather than 2 or 3-dimensional. And so we used 1D convolutions. And other than that, our model is very similar to a sort of a classic convolutional neural network.
And did you build it up from kind of scratch, or did you start with a deep kind of existing deep network architecture?
No, it's actually a pretty simple classic architecture that I built up from scratch. So essentially, it's just convolutional layers followed by max pooling layers for, say, 10 or 12 layers deep. I don't remember exactly how many layers we used. Followed by some fully connected layers, followed by the output, which is the probability that this particular input is a planet.
And did the model evolve much at all as you began working with the data, or did that initial model that you kind of settled on kind of hold throughout the project?
Probably the biggest change that we made over the project was actually to feed in two separate representations of the light curve that we were looking at, of the event, I should say, the event in the light curve that we were looking at. So this one of these was a wide view of the event, and the other view was a very zoomed in narrow view of the event. And so what we learned was that the model sometimes needed some information that was very, very far away from the the event we were looking at in order to make its classification decision. And so that was sort of facilitated by feeding in a wider view of the light curve. But also the model needs a fairly fine-grained look at the shape of the light curve of the event as well. So as I mentioned, we were looking for U-shaped patterns, but there are various other astronomical events that can cause, for example, a V-shaped pattern. And so what we did was we ultimately ended up feeding in two separate representations of the event into the model. And so each representation is treated by sort of individual convolutional layers that are totally separate, and then they're joined up towards the end and combined together to give the final output prediction.
Okay. And maybe tell us a little bit about like how the time has been allocated, like since that 6-month mark when you started applying the neural network.
Right. So we spent a lot of time last year writing the paper. So some of the things that we did for that was come up with various ways to visualize the sort of things that the model had learned. Especially as this paper was going to be published in an astronomy journal rather than a machine learning journal, where people are perhaps not quite as familiar as the machine learning community in what exactly a convolutional neural network is and what it's doing. So we used some techniques, for example, to visualize the features of the input that the model had learned. And that was also a good sanity check for us to make sure the model was sort of looking at the right features in order to make its decision. So the technique we applied there, which is quite a simple one, is if you block out part of the input and then feed the input into the model, and then you look at the model's prediction, if the part of the input that you blocked out was really important for the model's decision, then the decision is going to change a lot. But if you block out sort of an unimportant region of the input, then the model's decision is not going to change, at all, perhaps. And what we found was when we blocked out the regions that were that certainly we thought indicated that a planet had passed in front of the star, the model's prediction changed from predicting this was a planet to predicting it wasn't a planet, which was exactly what we had hoped. It means that we weren't sort of fitting to other aspects of the light curve. We were really fitting. Our model was learning the features that we expected. So we spent quite a bit of time really digging into the model and producing sort of visualizations and explanations of its predictions to put in the paper.
Awesome. And you're going to be publishing some additional information about that this week. Is that, do I remember correctly, you're going to be publishing some of the code that you used as well?
Yeah, that's right. So we published our paper this January, which outlines everything that we did. But this week, we're actually releasing all of the code that we used to train our model, which also includes actually all the code you need to download the data from NASA's servers to process the data in the exact way that we did in the paper. I mentioned like fitting away the low frequency variability in the star's brightness. That's included as well. All of the specifications for our model are included, and the hyperparameters that we use to train the model. And so anyone will be able to download this data, will be able to train a model, and potentially they'll be able to use this to go searching.
That's awesome. What are you hoping, if anything, to see out of this?
Well, a few things. I'm hoping that some people are able to perhaps build on the work that we did. So, as I mentioned, our project has been focused on data from NASA's Kepler telescope, which has been in operation for eight years now. But there's another telescope launching this year or it's at least scheduled to launch this year by NASA, which is called the TESS, TESS satellite. And that is going to use sort of a very similar approach to the Kepler satellite for recording this brightness data for many, many, many more stars even than Kepler did. And so I'm hoping that others in the astronomy community will perhaps build on this code that I'm releasing, and perhaps even apply it to other missions, and use it to discover planets in data collected by the TESS satellite, for example.
Awesome. Well, that is some really amazing work. I appreciate you taking the time to share it with us.
Great. Yeah. Thanks a lot for having me on.
All right, everyone. That's our show for today. For more information on Chris or any of the topics covered in this episode, you'll find the show notes at twimlai.com/talk/117. If you have any questions for Chris, please post them there and we'll make sure to bring them to his attention. If you're new to the pod and like what you hear, or you're a veteran listener and haven't already done so, head on over to your favorite podcast app and leave us your most gracious review and rating. It helps new listeners find us, which helps us grow. Thanks in advance. And of course, thanks so much for listening, and catch you next time.